Okay, so let me start presenting. Okay, so today the topic
Yes, sir.
is today the topic
You can
is
share
on
your PPT, sir.
advanced VLSI circuits. Okay, basically advanced VLSI. I'm trying to see VLSI is a very vast domain. I'm going to
Sir,
speak
PPT
about.
not share. Sir, PPT not share.
I'm sharing the PPT once.
Yes, sir.
So where did that go? Okay, I think it should be 21st. This one.
Session started.
21st. Into long term enter. Okay. The 21st. Is it not showing? 6 days PPT. I'll show the entire screen, no problem. Are you able to hear me? See my slides? Hello?
Yes, sir. Yes, sir. We can able to.
Yes, sir.
Okay.
Yes, sir.
Okay,
Yes, sir.
fine.
Yes, sir.
So basically, VLSI is a vast domain, right? I'm going to speak about one topic which is close to my heart, and that is the basic building block of VLSI. So I'm going to start with the standard cells, and then I'll touch upon the memories. Okay, because these are the two things which actually are several times asked in the interviews and all. And I also am an expert in these things, so I'm going to focus on this. Okay. Okay. So how many of you know the about standard cells?
Yes, we know, sir. Standard cells.
Okay. So why do we need that? Can one or two people tell what do you, why do we need standard cells if those are not there, right? What would happen? If we didn't have the standards, how do we build the ASIC chips? Do you know how many millions or billion of transistors when we do a latest AMD or a Intel or NVIDIA processor? Any idea?
Yeah, the complexity will be very high, sir. Because of the more functionality as per the consumer demand, every chip will be having lot of functionalities. So that the complexity of the design will be very serious issue at that time if you don't have standard cells.
So basically, the thing is, even though in human psychology also it happens, right? See, there is a thing called when we are doing from Narendra Modi level, what it interacts with the MPs, not on the MLAs, right? So basically, what happens is as we go up and up, there has to be a hierarchy maintained so that we can do a proper design, right? So okay, now let's go, get top down approach, right? So now this is a typical synthesis flow. Okay, so what do we mean by synthesis? Any idea? One or two guesses? All of you know what do we mean by synthesis? Can I get some answers? What do you mean by synthesis in VLSI
To
technology?
get the total count of the transistors in the cell, synthesizing the
No.
Preparation.
Yes. I hope
Preparation of
all of you would be exposed to something, ASIC technology or something. If not, okay, let me just explain. Okay. So basically, synthesis is nothing but, so okay, let's start from example. When we are using a chip, right? First, it will be at an abstract level what that chip needs to do. So the marketing team will tell the the design team that hey, we need so and so features. so many reads, so many writes, so many other multiplication functions. Okay, that has to be there. Now from that, it will be, the hardware will be prepared with the block diagram, right? What are the functionalities? Now after that, functionalities are written in a system level language, like system Verilog or Verilog, that gets into synthesis. Now that's by synthesis, what do you mean is, it will map into some feasible blocks. So if you see here, so this is a code, right? This is a like C, C++ or system Verilog code. Are you able to see my mouse moving?
Yes, sir, we are seeing.
Yeah. So that is the high level synthesis. Now you can see in the right side, you can see several blocks, some multiplier accumulator blocks, some adders, some buffers, and some multiplexers, right? All these things are there. So this is called high level synthesis. Then comes the logic synthesis. So this logic synthesis, what it does is, from these high level modules, it breaks them into small parts, and there you put it into the cells which are available in the standard cell library. Okay, so basically it comes to some plops, NAND, NOR gates, maybe some adders, full adder, half adder. Those things are also part of the standard cell library. Okay, and after this is done, this is called logic synthesis. Okay, so now once this synthesis happens, right, then comes the physical design. What do you mean by physical design? A lot of people also name it as back end design. Okay, till this is front end, till this high level synthesis is front end, right? People, you would have seen any companies, right? They'll tell I'm working on front end. Some people will tell I'm working at the back end, right? So till the high level synthesis is this front end. After that is the back end. Okay, what do you mean by back end? So basically, these are the things where lowest level things. Finally, so what is given to the fabrication, right? A GDS. I hope everybody understands, right? So any design, any chip you do, finally you need to give a package to the fabricator, right? Like last lecture we had seen, right? We had multiple fabs. One was TSMC, one is Intel, and in India we are going to have the Tata foundries, and presently we have SCL Chandigarh, right? So to the foundry we will be giving a GDS. Now we have a high level logic, right? From there we need to convert it to GDS. How does that get converted? That is through this physical design, right? So basically from these gates, it has to come to this lower level, transistor level, layout level design. Okay, now let's go to the what do you mean by the physical design, right? So now when we have, so basically we are now breaking down this part, right? So we have now converted the high level logic to lower level logic, where each cell, each of these logics is mapped to a available standard cell. Getting it? So now from that, we are trying to do a partition. Means, what do you mean by partitioning? You have to do a, you need to do a pipelining, isn't it? Like, all the functions you cannot do in a single clock cycle. You need to partition into multiple clock cycles, right? So that is called partitioning, right? And then after you do that, you need to do a floor plan and placement of the cells, because based on where your critical path is, you need to reduce that path, right? So you need to first place the standard cells which are mapped into the proper place in the chip, right? And then you do the routing. Means, what do you mean by routing? The inputs are signals from one cell would be connected to the outputs of the another cell, and vice versa, right? So this is how the physical design flow goes, right? And after you do the routing, you need to fix the DRCs. There are design rule checks, right? So once you do that, once all the DRCs are clean, then you go for the tape out, right? Okay. Now let's see the attribute of a standard cell, right? So this is a typical template of a standard cell. You will have a power bus and ground bus. Can anybody give a reason why we need a BDD and ground bus? Why, if it is not there, what would happen? Can anybody answer? Am I audible?
Audible, sir, audible.
Okay. So anybody can tell me why we need a bus of BDD and BDD BSS, bus for BSS, and then NWL area and PUL area? Any idea? If it is there, how does it help? So basically, you should have seen the previous diagram. What you are doing when you are doing the standard cells, we want to abut them each other, right? So here, if there is a cell like this, BDD is up and BSS is down, you abut the next cell, BDD get connected, because what we need, power to be connected, right? And ground also should be connected, right? So that's why these two buses are continued. So these are metals, right? Then in a typical CMOS technology, you will have the PMOS at the top and MOS at the bottom, right? And now if you imagine this one, next row will be sharing the VDD with this one, right? And so it will be flipped, right? So, and there are different heights of the standard cell. One is 90 cell, one is 12 T cell, one is 60 cell. Any guess why we need higher height, and what are the advantages and disadvantages of higher height? Can anybody give a reason why we need multiple heights of the cell? Any guess? If we increase the height of the cell, what are the advantages we are going to get, and what are the disadvantages also we can get? Okay, fine. We will get you ask me this question after 2-3 slides. Okay. Now let's see what are the types of cells in a library, right? So we have combinational cells. Any idea what is the meaning of combinational cells and what is the meaning of sequential cells?
I think everybody knows digital electronics. Everybody knows.
Everybody knows. Okay, nobody's answering.
Combinational logic and sequential logic is
So basically, wherever there is
digital
no
electronics.
clock, right? In output is a function of only the input, that is called combinational, right? Whereas sequential is output is a function of the input, present state.
Cascading, it may be cascading.
Cascading is not sequential. Okay. When the
output is output not only depends upon the present input but also the past output. That past output will be stored in a memory. So those memory elements are actually called the flip-flops, and that particular unit is a sequential logic.
That is correct. That is correct.
Correct. Now, anybody knows what are the tap cells? Okay, let me explain. So now, till 2000s, right, we didn't have the tap cell concept. But since last 20 years, we are using the tap cells. So every standard cell in the library will not have the connection to the well. Okay. So any standard cell library you pick up from last 10 years, they will only have the power rail and ground rail. There will be no connection to the well. And without the well connection, you cannot pass the LBS. So layout, LBS means, right, layout versus schematic. Because you need a bulk contact for the cell to pass LBS. That is where the tap cells come into picture. Okay. So these tap cells will be connecting to the well, right? Then only your total connection becomes pakka. Okay. And that is also tap cells also need to be placed at a regular interval. Okay. Now let's come. What is the pillar cell? Any guess why we need pillar cells? What is the structure of a pillar cell? Any idea?
Used to fill the space.
Yeah, basically these are the spacers. Why you need a spacer?
Yes.
Because see, sometimes you cannot, you will have some area where you cannot put any logic. That's the spacer, right? So that is called the pillar cell, right? Then there are decap cells where basically you you provide some caps to the power rails. Okay. Then spare cells. These spare cells are actually concept from last 10 years or so. So basically these cells will have some metal connections, but they will not be connected to the to the signals. Okay, these pair cells basically, suppose you want to do some logic change later, you can use of this, make use of these pair cells. Now, what are the tie cells? Any idea? So tie cells are basically the cells where the output of the cell will be either logic 1 or logic 0. Why do we need it? Or let me reverse the question. If we don't have the tie cells, if we connect the gate input of a cell to power supply directly, do you think it is a good idea or it's a bad idea? Or even ground to the direct ground? Any idea what are the merits or demerits of connecting the power or ground directly to a gate? Okay, I'll just tell you. So it's actually a very bad idea, since past 1 decade, we are not allowed to connect any power or ground to the gate of cell, because during fabrication or during this chip starting, right, this power and ground go through multiple, what do you say, cycles of glitch, or basically there will be some disturbance in the power and ground, right? So if you connect this power and ground directly to the gate, then it can damage the gate. And you know the way the VLSI circuits work, right? If one transistor also goes bad, unless you have a redundancy, the entire logic can fail. So the chance of failure becomes more when you connect the power or ground directly to the gate. If you connect to the diffusion, the damage is much less. But if you connect to the gate, because it's not it's CMOS logic, right? It becomes very bad. Okay, that's why you need these tie cells. So these tie cells will be basically by construct connecting the output to the 0 or 1. Okay. Now there is something called delay cells. So these delay cells basically provide some delay. Sometimes you need to pick some hold violation. Say you need to delay the clock signal, right? And similarly, you have a set of violation. You need to delay the data signal. Okay. Now there are integrated clock gate, right? What does that mean? Why we need it? We need these clock gating circuits for low power, because if you don't get the clock, then the clock will be switching. There will be several inputs and outputs which will be switching, and that can cause an issue. Now there are something called end cap cells. These are again last decade or so. Basically, these cells will make the so when you are doing a chip, right, towards the end of a region, you need to end with some cells, okay, so that the entire chip as a macro becomes DRC clean. Okay. And then there are antenna cells. I hope you guys know what is the antenna effect, and what is the antenna issue. Is it understood in the basic VLSI circuits? Gate to drain ratio or something? Okay, let me just explain. Okay, so while manufacturing a chip, right, you will have multiple charge deposition on the gate, on the metal. Okay, and now there is a phenomena called antenna effect. So like you comb on the hair and put it close to some pieces of paper, what happens? It gets charged up, and then it attracts the papers, right? Similarly, during the fabrication process, your metals, they collect some charge. Now if they are connected to the gate, that becomes a problem. So basically, for every transistor, there has to be a gate to diffusion ratio. Okay, for every piece of metal, if it is connecting to a gate, it has to have some significant amount of diffusion connection also. Then only it becomes less risky. Otherwise, during the fabrication process itself, it may damage the gate. Okay, so that's why we create all these antenna cells to add more diffusion area into the cell, so it becomes fabricatable. Okay, so now let's see some combinational cell examples, right? Gates, right? AND or NAND or complex gates like multiplexer, half adder, full adder, AOI, OAI, right? Clock tree cells, delay cells, all these are combinational circuits, right? And then these things in violet color are the sequential cells, flip-flop and latches, cannibal flip-flops, right? Okay. So now let's just briefly touch upon some of the layouts. And from the advanced VLSI circuits perspective, I want to focus on some, good layout, features, right? Now, say when we are doing a NAND cell, right? What happens? Can anybody guess, how the NAND is getting formed? So NAND means what? Your PMOS will be in parallel or series. When is it NAND? Your NMOS will be in series, right? And PMOS will be in parallel. That's what you can see. Here, if you see, the output is connected between the two gates, right? So each of these is a poly, right? So the output of this cell is connected to the two gates, right? And the inputs, the other input is connected to BDD. So basically, these two are in parallel, right? Whereas here, if you see, the output is this side, then the next one is not connected to anything, and the other one is ground, right? So this is called series, right? So this is a NAND gate. Now I can ask, I'll just ask you one thing. So which metal piece will have maximum current during charge up? What happens when you want to do a pull up? Which metal piece conducts most current? Can you guess? If we are seeing, so can you see my mouse? So your output is this one, right? This node. This is going as the output. Now, when you are charging up, it gets from this output, right? And goes all the way like this, right? One from this piece and another from this piece, right? So it is a parallel path. So from here to here, the current goes, right? And when it's pulling down, it goes through this path, right? So now there is something called electromigration. So when a cell goes through thousands or lakhs of cycle, it creates a damage in the cell. Like say, if you have a piece of metal, if you do a rubbing and use it several times, even in wires also, you would have seen after 10 years, 15 years, it gets melt, right? Because these cells conduct a lot of current, right? Ultimately, it's a piece of wire, like you have a wiring in your house, right? So what happens is the piece of metal which carries the maximum current, that goes through maximum wear and tear, right? So the key takeaway here is these common output nodes you need to make a thicker compared to these ground and BDD ones. Okay. So now if I come to the NAND 3 input, I hope you can understand that. Your this one and this one in parallel, and the other ones are in parallel, right? Okay. Now let's understand what are the figure merits of a standard cell. When do you tell that a standard cell is good? Can anybody guess? Area. You need more area or less area to tell a cell is good or not?
Area.
Suppose, which one?
Less area.
Less area. Delay. You want more delay from a cell or lesser delay?
Short delay.
More delay?
No, short delay.
Short delay. Yes, less delay. But again, there is a catch here. If you are creating a delay cell, then we want more delay. If you are creating a simple logic, regular logic cell, we need lesser delay. Power, we need more or less. If a cell draws more power, is it good or bad? Any guess?
Good. Good.
If it is more power, it is bad, because imagine a cell takes say 100 nanowatt. If the same cell takes 200 nanowatt, you have thousands of these cells. It goes, the chip might melt also, because it does so much power, right? More the power, more the heat, right? Like you can just take it analogous: a 1,000-watt bulb and a 10-watt bulb. Which one will get heated more? 1,000-watt, isn't it? So same thing. The power, you want it to be less. Okay. Now input cap. So any cell, there will be input, right? So somebody has to drive that input. Now when the cap is more, that means it will be loading the other cell more. So you want this capacitance of the input, looking at the cell, to be less. Then there is something called legalizability. These are the advanced concepts. Now, if a cell you design, but it is not, ultimately I had shown the floor plan, right? The cells will be stacked together, right? So if the cell doesn't fit well in the entire structure, then we tell that it's a legalizability issue, right? So we want the cells to be legalizable, but always it's not possible to legalize at each and every place. So complex cells will have a legalizability percentage of say 10% or so. That's still okay. Whereas, but at least 10% should be there. Legalizability means what? Out of 10 different scenarios, it should be able to at least fit in one scenario. Okay. Now, drive strength. What do you mean by drive strength? Suppose a cell is driving 10 cells and it doesn't deteriorate the signals, rise or fall time. That is good. But if the cell cannot drive that much, even at 2 fan out of 2, there's a fan out concept, I hope you understand, right? So if a cell is driving similar cell two times, two of those cells, and still goes bad, then we tell that the drive strength is not good enough. Okay, so we want the drive strength to be good. Okay, now what are some of the collaterals of a library, right? So when you design a library for the cell, we need a GDS, because that's the final output from a cell. Okay, now there's something called a LEF, right? So any idea why? Anybody has understood, come across this concept of LEF or abstract views? Anybody knows what is an abstract view in a library? Okay, let me explain. GDS will have all the metal layers, all the even base layers, everything will be there. But that is not needed for the placer. The placer just needs the metal layers, because ultimately it will stitch the metals, not the base layers. Base layers means this the enwell, poly, diffusion, all those layers are not required for the place and down. Finally, ultimate chip will go to the GDS where all the layers will be visible. But the labs will have only the metal layers where the input pin is, say, for example, in this one, right? So you will have an input pin where there will be some output pin. You just need to know those locations, right? And the rest all locations will not be visible. So you can route with that. It will be a much. So if you are flooded with lot of information, you will be slow. The router cannot route. But if the router knows where the pin is, where the blockage is, it can route easily, right? Because it will be easily, it gets the information it requires, right? Okay. So now some of the attributes of a lab is, for example, this is an AND cell, right? It will tell that it's a core type cell. The origin information is required. Then the size means what? This is X and Y, means what is the width and what is the height, right? Then what type of site is. So basically these are the examples. When you open a lab of any standard cell library, you will see this. Okay. Okay. So now let's just understand, what are the some of the collaterals. Okay. So I had actually explained here, right? You need left timing views. Okay, let's now understand what are the timing views. Anybody can guess what is the timing view? What is the meaning of timing leaves? Anybody has has an understanding what a dot leaf is? Okay, fine. So a dot leaf. So basically, when you are doing a standard cell, right, you need some abstract, description of the cell, right? So what a dot leaf will do is, when the scenario, user scenario can be different, right? The input load or input slew might be different. The output load also might be different. So for different input load and output slews, it will try to characterize the cell, and it will give the thing when it will give some kind of a lookup table, right? And from there you will find the actual delay behavior, right? Ultimately, say, let me explain you from a NAND inverters, for example, right? So when you have a, okay, let's see an inverter, no? Okay, say you have a NAND gate, right? So now when you, so this cell has input and this is output, right? So your input could be a very sharp input, or it could be sluggish input, right? And the load here also, it could be driving one cell, it could be driving 5 cells based on, and it could be driving a big wire also. Based on that, your load and input flow will be varying. So for all those scenarios, you need to characterize this particular cell, and that information will be storing as a dot leaf. Okay, that's what we are calling a dot leaf for the cell, right? So that will also have the power information. Okay. Now, so basically it will have the delay, power information across multiple PVT corners, process, voltage, and temperature corners. Okay. Now, can you guess why we need a Verilog view for a cell? How many of you know Verilog? I think it's part of basic VLSI, right? Digital VLSI. Okay. So for any standard cell, right, we need to abstract it through a Verilog, so that the functionality testers, right, ultimately you need to synthesize. So for that, Verilog input is Verilog equivalence is needed. Then there is a serial netlist, means the schematic netlist. Spice netlist will be when you do the layout of the cell. It's it's parasitic extracted in an output is called SPEF. So that is required to characterize the cell, and also if somebody wants to do a critical path analysis, you need the spice netlist. Okay. Now there are some other advanced views like Apache views, where basically you give the cell from the power side how much power it draws. Okay. Then there are electromagnetism views, where basically you need to give how much toggle it the cell can take. Okay. Then there are several advanced views like DFT views, where you give an file. Okay, it's a mental graphic model, and UDFM views. Okay, so these things are there in a typical sub 5 nanometer library. Okay. Okay. So now let's understand what is the IR drop and why we need this analysis. Anybody knows what how the signal EM and the IR drop analysis things go? Okay. So in a typical chip, so this is the IR drop analysis for a typical chip. Okay. So now if you see, so there is a color code. Okay. So if it is green, it is good. If it is yellow, it is little worse than that. If it is violet, it's okay. It is orange, it's bad, and if it is red, it's almost bad. It can go bad anytime. Like it can melt anytime. So as you can see, it goes through this, and then you can see there. So this is a first level, and then after some time it goes through. So here you can see after multiple uses, for the electromagnetism. That means now the metal gets melted. Okay. So this is the intent of the airdrop analysis. Okay. So what we do it in simulation and then give a heads up. Then what you do, you change the circuit, you do better the standard cell which is used here, and then improve it, and then make sure that in the simulation you don't go to this bad. Okay. So this is part of the standard cells. Okay. So I would like to then touch upon one more thing, that is fault memory. Okay. So for memory, I have ready-made slides available. So I'll just go through some of the slides. You give, interrupt if there is any doubt, right? So why do we need memories, right? So memory are the storage elements, isn't it? So like, memories, one good thing is that they can be arrayed, right? So now if you see here, okay, so these are some of the classification of the memory arrays. You have RAMs, right? And then that comes into static RAM and dynamic RAM, right? Whereas there are also ROMs which are non-volatile, and then multiple ROM options are there. And then you have serial access memory, content accessible memories. So all these are one field actually. Okay, multiple companies, some companies do flash ROM, like say SanDisk and all, they do flash ROM and non flash ROM, right? Whereas multiple DRAM companies are there, like Micron, right? SRAM company, most of the chip design companies will have SRAM. Okay, now we'll go to the typical architecture of a memory, right? So now, when you are doing an array, right? What do you mean by array? Any guess? You will have a row and column, right? Basically,
Column.
yeah. So you have so basically things will be in a row and some things will be in a column, right? So now, when you want to store access a memory here, so now this way you will be storing the memory. So while storing the memory means what? You'll be writing into the memory, right? So how do you write? So basically each row is accessed by a word line, right? So this will be connected as, with gates, or physical implementation could be different, but I'm just telling the basic philosophy, right? So each one will be connected through a word line, and the vertical ones will be connected through bit line, right? And to access the particular word, we have to do go through a row decoder, and for the column we need a column decoder, right? Got it? So this is how it is regularity is maintained, right? Okay. So now let's see. What do you mean by SRAM cell, right? So SRAM is static RAM, right? So if you see here, what happens here is you have a back-to-back inverter circuit, right? And then you have a you have, for example, now to write, you have a signal here, and the opposite of that is right bar, and read bar, right? You get it? So how many transistors will be there here? 2 plus how many here? 4. Okay. So 2 plus 4 plus 2 plus 4, right? 4 plus 8 to 10 to 12. Why 4? Because you have this enabled one, right? So now if you see a 60 SRAM cell. Okay. So here if you see any more memory logic will have a back-to-back inverter for sure, right? So you have a back-to-back inverter, right? So now you have these both the outputs connected to two lines. These are called bit line and bit line bar, right? And this is called the word line, right? How do we read and write? We'll just go through that slide again. So to read, what we do? We precharge, right? So this is called cross-coupled inverters. Okay. To precharge, what we do? To do a read, what we do? We precharge both bit and bit bar, right? So when we precharge, what do you mean by precharge? We make them one, right? When both are one, then what we do? We connect the word line to high. So if you have a stored 0 here, right? This particular one will discharge, right? So this bit will go 0, and then we know through the bit line sensing that there's just 0 stored here, right? So you can see that logic here. Okay. So when the word line is rising, right, this bit line is coming down, but now there is a bump here. That bump is coming because when this is rising, there's a coupling. Nothing is ideal in this world, right? So when this input is rising, there's a coupling gap between this and this signal, right? So that is making this to rise. So that means you have to be careful. If this one goes beyond a certain level, this will not behave like this. Okay, so that's why it's called. So this one, for this one to be lesser of an amplitude, you need a read stability. That means a node should not flip. If this one flips, it will flip the other one, right? So from that you need a sizing information that N1 should be much greater than N2, right? So that means this down node, right? Pull down transistors, these and these need to be bigger strength than N2. Okay. Yeah. So similarly, writing, what we do? So while writing, what you need to do? We have to store the bits into this transistor, cross-coupled transistors. So what we do? First, we give wherever we want to write, right? We need to make that bit line to be high, other one low. Then we turn on the word line, and then what it writes the proper one to that signal, right? And for this also, again, there is a glitch condition here. If you see here, so if this signal N2, right, is not enough properly sized, this one will give a opposition, because when you are writing, right, this one gives an opposition, because you might have a situation, you would have a 1 here and you are trying to write a 0 here. 1 is here means what? This PMOS is keeping it high, right? So if so while writing, what you have to do? You are forcing a 0 from here, whereas this is forcing a 1 here. So if your N2 is not good enough than P1, then it cannot write. So that's why you need a write stability or writability. For that, N2 should be much bigger than P1, right? So N1 has to be bigger than N2, and N2 should be greater than P1. That means you need to size it properly, right? So that's why it is called, this has to be the weakest, this has to be medium, and this has to be strong. Okay. So now when we are doing a column decoding, what we do, then so we had seen till this, right? So next one, what happens is multiple of these will be connected together, and then they will be connected to a column selector. You need to then connect it to a sensor, right? So that bit line turning high will be happening through a bit line conditioner. Okay. So and this is the timing signal. So if you see, when the word line is going high, bit line will go low for the 0, 1, and then these outputs, right, the buffer output will become corresponding 1 or 0, and based on that we detect. Okay. Similarly, write operation was also done. right? I would encourage you to go through that. Okay. So now the layouts and all, I think we should skip for the lecture. And now, what is the decoder? So whenever you're having these, read, the word lines will be there, right? So we need a decoder circuit, isn't it? Because this will be like a you cannot turn on two of them high. You need to turn on only one of them high, right? That's the role of the decoder, right? So then there are multiple aspects of the layouts of the decoder. Then there will be large decoder. When you have n equal to 4 means you need to do multi-stage decoder, right? And there is something called pre-coding. Okay, so where we just consider half of them to be 0 and then consider the other ones, and vice versa. Okay, I think beyond that would be a little complicated. I think with this I'll just take the questions. We have 10 minutes for question answer, right? Hangabal? Anybody wants
Yes,
to
sir.
have a question? Yeah.
Yes, sir.
On the standard cells or memory part, any questions?
No, sir. It's very much clear.
Yeah, any other questions?
So the link for the memory thing, I'll just post. I didn't feel any need for the slides for the, because this is a very good slides are there, right? So I'll put in the group, but the other slides I'll share, because the standard cells you will not find it in the regular. Yeah.
Sir, any other questions? I think. Hello, sir. Hello.
Yeah.
No, sir. No, sir. Everything fine.
Is fine. Okay, then let us. I think faculty members and I think everybody is enjoying this talk. Is a VLSI technology is based on the all transistors, logic gates, sequential logic gates, and the combinational things.
Yes, sir. Yes, sir. It's very
I hope
interesting
any
talk,
doubt,
sir.
any clarification.
Yes, sir. Very basic things. It's really helpful for us in the research level. Thank you very much, sir, for your nice talk.
Sure.
Okay. Okay, then let us thank Pratap sir. Is a very excellent talk.
Thank you.
Almost